Hi all, I'm Raghudara, and I'm head of data science at the transportation trucking unicorn Keep Truckin'. I'll be talking today to you guys about why you should be using Apache Spark. So it's no secret that big data is a real talking point. There's quite a few organizations built around providing big data services to clients. In general, there's a lot of people knowing that they must be collecting this information. I think it's well summarized by this Dilbert cartoon about why big data is important, but also the general misunderstanding about what is big data and why is it useful to people. I think there's four major reasons why the big data analytics niche is booming. First of all, there's increased awareness of data as a primary differentiating factor for companies. Companies know that in order to maintain their edge, they need to be leveraging their data. This is now common knowledge within orgs big and small. It's also known that the more data you're able to leverage, the theoretically at least, the more superior your machine learning models and inference frameworks become as they're given access to additional training examples. Cloud storage and elastic compute services have become relatively cheap, especially in recent years, and people are able to store vast amounts of information on the cloud for not much, and they're able to crunch this data in a way that doesn't break the bank. But the fourth point is the topic of today, which is powerful and familiar feeling analytics utilities have emerged, which allow customers to leverage the power of big data without it being a foreign and complicated exercise. And perhaps the foremost amongst those utilities is the rise of Apache Spark. Um, Apache Spark was released in 2014, and since then has quickly become the de facto standard for big data operations for data scientists and engineers. Uh, it obviously, as you can probably guess, has support for big data operations, but also a lot of ancillary utilities for topics such as machine learning, data streaming. It supports a wide variety of data connectors, some of which are visualized in the diagram there on the right. Um, and because of all of this flexibility, Spark truly is one of the most versatile tools for leveraging data at scale. And it's very likely that many in the audience have heard of Apache Spark, but what exactly can you do with it? First and foremost, you can wrangle mind-bogglingly large volumes of data with relative ease. This data can live in a variety of places, from traditional RDBMS systems like Postgres or MySQL to data warehouses like Snowflake, Redshift, BigQuery, uh, flat file data lakes, things like Parquet and Delta Lake living on top of resources like Amazon AWS S3 or GCS on Google Cloud, and document databases like Mongo or Dynamo, but even other NoSQL variants like graph databases. So there's a vast variety of drivers for upon which Spark can be leveraged. Uh, Analysts can use libraries and frameworks that are comfortable and familiar for them. They can use PySpark, which, as we'll see in short order, is very similar to frameworks that people are already comfortable with, or Spark SQL, which is a SQL variant that for vast majority of analysts will come very naturally, as it is essentially mainline SQL. Uh, you're able to train machine learning models on enormous data sets using MLlib, which is an add-on for Apache Spark. So you're able to do machine learning models and inference at a very large scale without needing to use any hacky tools to make existing frameworks like sklearn stretch to meet that data demand. You can process real-time data using structured streaming, Spark streaming, and you can even model enormous graph networks using, again, additional Spark add-ons like GraphX. And this is just a small sampling of the kinds of functionalities that Spark enables. And this, again, should be stressed, is all built upon the same core framework of Apache Spark. So to accomplish these kinds of tasks, and as we'll see, uh, these kinds of data transformations, you don't really need to piece together too many additional services. I'm not going to pretend that we have time to cover exactly how Spark works in this presentation. Suffice it to say, it is an in-memory MapReduce paradigm. What that means is, unlike Hadoop, which Spark, both Hadoop and Spark are MapReduce based, but Spark has largely replaced Hadoop as the preferred compute framework for big data. Spark is quite memory heavy, so a lot of the transformations that you would do and the transform graphs that Spark executes when you provide it a job, a lot of these run in memory, which helps sort of, well, I guess it feeds into the mindset that Spark does require a lot of RAM, especially when compared to Hadoop. And this is definitely a true statement. Um, Essentially, how Spark works, though, is there's a driver and there are executors. The driver contains the Spark context, and this is essentially the root of the operations that Spark is about to execute. Then, using an intermediary cluster manager, Spark is able to communicate with compute nodes. And the nodes themselves run multiple actual workers, and these workers are called executors. These are what actually accomplish the task that you're trying to do. And the executors on a node might divide up the work for a task. For instance, if you're trying to MapReduce a function on a set of files, each executor might be tasked with handling a few of the files. And in this way, you're able to massively parallelize and compute atop the data. And the point of what makes this very suitable for elastic compute is that these nodes can be VMs or they can be entire instances. So if you're familiar with cloud frameworks like AWS or GCP, this would be, for instance, what you'd call an AWS EC2 instance. And you could have multiple executors running on a node, which is the instance. You can also, in Kubernetes, which has arisen quite recently, Spark on Kubernetes as an alternative framework for doing this kind of computation. These nodes again are containers, are pods, and then you can have multiple containers running atop these, and potentially run a bunch of these different pods on the same physical node. So there's a variety of different ways you can architect Spark workflows, but they all have this core structure. I think it's useful now that we've seen what you can do with Spark and what kinds of utilities it works with. Let's actually go over some concrete use cases for what you might be able to accomplish. And it might be useful when looking at these to think about how you might pattern match some of the workflows that you have in your day-to-day to a workflow that is aligned closely with the ones demonstrated here. So here's one very common example. This is one that we use extensively at Keep Trucking, where we have petabytes of information stored on the cloud and multiple machine learning models that need to be updated from this data. And this data is constantly being added to from a large variety of, in our case, it's vehicles and trucks on the road. But in other applications, it could be IoT data from different sensors, different elements of the supply chain, pushing data to some sort of data lake, data warehouse, some data structure. So in this case, let's assume that the data lands in an S3-based data lake. But you also want to leverage crucial metadata about these assets. And this lives in a transactional table, let's say Postgres. And again, our goal is to update a machine learning model daily. So the way you can sort of piece together an architecture for accomplishing this, and I should stress, this is very much simplified, but it's more, the premise of this is to show how Spark can sort of play a central role in accomplishing tasks of this type. Of course, the nitty-gritty is a little bit more complicated than appears here, but fundamentally, this is a very viable stack, and is one that Keep Trucking actually uses to a large extent. Spark, again, as we saw from a previous slide, has community-based drivers for a vast array of different data sources. And these data sources, of course, include Amazon S3 and Postgres. So Spark is able to connect to these two and pull data. And MLlib, which is the machine learning library, which is again an extension of Spark, can be used to actually train this model. So you could train, for instance, a gradient boosted tree, um, or any other type of classical machine learning model using MLlib. Uh, you could then schedule this workflow to run, because the example use case here mentions running this workflow daily. So you could use an orchestrator such as Airflow to schedule and run this training task on a daily basis. In order to serve the model that's ultimately produced, you can use a serving framework. For example, Kubeflow. Kubeflow can serve a vast array of machine learning models. You can even cross-compile models from things that are Spark enabled to non-Spark enabled. All of this can run inside a Kubernetes environment. The portions in the dotted rounded rectangle over there. Uh, and it's important to stress the rise of Kubernetes. Again, I mentioned earlier, but Kubernetes is really allowing people to stitch together pretty complex serving frameworks with relative ease, especially through the use of Helm charts, where you're able to deploy an entire service in just a couple commands. Airflow, admittedly, is not my favorite service. I mean, I think you'd be hard pressed to find someone who would say that it was, but it is a very useful tool in accomplishing this type of workflow. Let's talk about another potential use case for Apache Spark. So say that you wanted to run an anomaly detection algorithm against a stream supply chain transaction data. So maybe you're receiving transactions, they're coming in via some endpoints, or maybe you're using WebSockets to stream them in, and you wanted to run some sort of a windowed time-based anomaly detection algorithm against it. Simultaneously, you want to build a transaction graph that tracks, okay, what are the different elements of the supply chain and how are they interacting? So as you're processing and validating the transactions, you also want to build a graphical structure that'll enable you to do perhaps better visualization or understanding of the connectivity within your network, and perhaps enable more fancy graph algorithms down the line, like community detection. Um, Again, Spark can play a very central role in accomplishing this otherwise seemingly complex task. So if you use a service like Apache Kafka, which is one of the most common ways you can receive streaming data, um, you can connect this data stream to Spark Streaming. And Spark Streaming is able to accept Kafka as a data source, and you can ingest streams with certain time windows and bounds. So maybe you want to ingest an hour of buffered messages at a Kafka queue, at a Kafka topic. So you're able to do that. Maybe you read in an hour by hour, maybe you limit by message count. But once you have the data that you're looking for in a window, you can then apply in Spark your anomaly detection algorithm. And this algorithm, again, can take many different forms. You're able to import and use external libraries if you like. You're able to do anything you can in normal Spark. The fact that you're using the structured streaming doesn't really change what's actually happening under the hood. You can then perhaps persist some of your artifacts and logs from your anomaly detection to something like Amazon S3. Again, any sort of flat file store is very popular when coupled with Spark. This perhaps is due to how popular data lakes have become in recent days, but also the HDF, the Hadoop file system roots that Spark is also able to access and read from. And you can then use a utility like GraphX, which again is an extension for Apache Spark, which will then allow you to use a graph API to access the data and do big data operations against very large computational graphs. So you'd then be able to query, and you'd be able to do higher level analysis upon this graph structure. You, of course, don't have to use GraphX. Spark is compatible with Neo4j, which is another very popular graph database. So to be clear, GraphX isn't really a graph database, it's more of an extension. But if you wanted to connect Spark to a graph database directly, such as Neo4j, you're able to do that using, again, a nice community driver. So again, it's not so much Spark in isolation that adds a lot of value, but rather the extensive ecosystem that has been built around it, which enables people to perform very complex use cases with relative ease and have only a single tool sitting there accomplishing a wide variety of transform types and use cases. So the final one, and probably the most common and least complicated use case that I can understand for Spark is wanting to use it to accomplish interactive ad hoc analyses on large data sets. So imagine you had a large data set stored in a data warehouse, such as Snowflake. So let's say it's a retail data set and it's a very large transactional append-only data store data source. And what you'd like to do, of course, Snowflake isn't append only, but imagine that this is just retail transactions which are constantly appending to some table on in another batch process, potentially even using another Spark data pipeline. So there's you can use it in different ways. These are obviously workflows in isolation, but you're able to piece them together at will. Um, Notebooks, I think, for anyone in the data world, it's clear that Jupyter is the leader in that space. Although there are new competitors trying to take that crown, Jupyter is by and large, I would say, the major way that people are exposed to data science, even in the first place. Certainly was the case for me. In fact, I learned Python through Jupyter, and I actually prefer using it when I'm doing templating for Python, uh, even outside of data science or anything data heavy, just because interactive programming is an extremely powerful paradigm. I think most people know what this means, but just for the sake of clarity, by interactive, I mean you're able to execute a portion of the code. And in something like a notebook cell, view the output and continue to operate on the output that comes out of it. So it's often referred to as a REPL or read evaluate print loop, but essentially you're able to process data and workflows piecewise without needing to specify the entire job, have it be, say, compiled into bytecode and then run. There's obviously advantages to that approach as well, but interactive programming is very useful when you're first doing exploratory data analysis to make, for instance, partial plots or data frame transforms. But also, it's a great way to look inside the internals of a new module or library because you can do print statements ad hoc, you can see what's happening, and you can run experiments very, very easily. So if you wanted to run ad hoc analyses, you could, of course, still use Jupyter today, and you could bypass these two middle layers and have Jupyter talk directly to Snowflake via something like Pandas, which is, I would say, the most popular data wrangling solution in Python. The problem with this approach is that Pandas really is not designed for very large data sets. I think past a few million rows on most modern machines, it starts to really choke. Of course, if you have fewer than that, you shouldn't even be, thinking about using Spark. In my opinion, Spark really only has value at the 10 million row and above mark, is when you'll actually see real benefits over something much lighter weight, because Spark does have quite a bit of overhead, both in computation and in maintenance, as we'll talk about in a bit. But on its own, Pandas really does not have the horsepower to execute on large data sets. So if you're reading in a large table from Snowflake, or you wanted to do sort of Pythonic transforms, so things you can't do directly in Snowflake in Spark. So obviously you can do a huge amount of transformation directly in Snowflake using Snowflake SQL. But if you then wanted to use your favorite library in Python against it, well, you're out of luck, and you need to get the data into a Python environment. And this is where Spark really shines, because Spark has a Snowflake connector, and you're able to simply run via a jar, by the way, that you can install and mount to your Apache Spark environment. And you're able to then use a service called Livy. Livy is a REST API for Spark. It is another Apache project, currently being incubated, I believe. And if you string together Jupyter, Livy, and Spark, you're essentially able to get Spark notebooks. And Spark notebooks are a very, very powerful resource for those doing big data ad hocs. I would say it's the bread and butter of what we do at Keep Trucking in terms of how do we do ad hoc analytics and how do we actually see what's going on with our data. We're very, very reliant on Spark notebooks. And I would say any company that is also looking to do big data analytics is likely in the same boat. Um, if you're not comfortable stringing together these various utilities, there are vendors which provide everything you see in that dotted box. Popular ones are Databricks and Qubel, which offer some combination of Jupyter connected to an API server, be it Livy or not, connected to Spark. And so this is obviously a much nicer interface if you're interested in more just acquiring a piece of software that gets you the job done. Um, but having this understanding of what is actually going on under the hood is very valuable when you're trying to understand, what is Spark doing for me? It's actually allowing you to run interactive scripts, big data scripts, and this interactive mode that Spark has is really, really powerful and useful when you want to do ad hoc analysis at scale. So uh, I briefly alluded to earlier the fact that pandas and Spark are very similar, and I want to just drive that home by actually showing you some code that, admittedly, not the most functional code. If you read it through, as I assume many of you have already done, it's not really accomplishing the most fascinating things. I import a cube function from NumPy, something I didn't know existed before I started writing this. Um, and what I have done in both of these uh, code snippets is I've grouped by a column called A, and I've found the mean of the remaining values. I've then created a column C from the column B using NumPy's cube function. Of course, you're able to write this in primitives, both in Python and in Spark. Um, but I thought it would be useful to show that both of these frameworks can very readily, I mean, obviously people are likely aware that you can leverage NumPy and Pandas, given that Pandas itself is largely dependent on NumPy. But it's useful to know that just because you're dealing with Spark and big data, it might seem a bit disconnected from the rest of the ecosystem. But not only, if you look, the syntax is quite similar between the two, but also the fact that you're able to very readily use these NumPy or external library functions in your Spark code. So this is accomplished with something called a UDF, or a user-defined function, and this is just an inline UDF because we're just wrapping the cube function and then applying it on the column B. You're able to do much fancier UDFs if required. So it should be stressed that this code, whether it's to do split apply combine paradigms, whether it's to drop columns, whether it's to apply external package functions on top of data, it's very easy to do in either Pandas or PySpark. It's not that making a conscious decision to use big data systems, locks you out in this, land of austerity where you don't have access to the kinds of utilities and functions and libraries that you feel comfortable with. Is the UDF the most efficient thing? No. You should use it sparingly, and obviously this is actually a terrible way of accomplishing the cube root, given that there's, again, very nice, highly optimized Spark built-ins for doing the same job. But this is more to just show an example of the familiarity between someone who's well-versed in Pandas, which is, I'm assuming, many people who are interested in doing data and are maybe thinking about big data analytics. They likely already have some basis in Pandas. So I want to stress that the shifting cost, the cost of switching over to something like PySpark, is really not that high. This code is likely very readable to someone who's just come from Pandas land, minus maybe the UDF bit. So that isn't to say that Spark is free of all it has no pitfalls and it's the silver bullet to all your data problems. I've identified 4 major problems that I think plague a lot of big data deployments, having worked and having helped set them up for various companies in the past. Firstly, Spark is quite complicated to get started with and maintain. This is changing, but definitely still the status quo that is non-trivial to set up a Spark environment and have it be fully operational. There's a couple obvious solutions to this. You can use a vendor who will do this for you. So people like Databricks, or in your cloud offering, something like AWS EMR, Elastic MapReduce, will make your job a lot easier because they will manage the Spark nodes for you, which is a task not as challenging as the sort of diagram you see on the right of that horrible server wiring, but it can sometimes feel that way. The alternative solution is to use big data consultancies. There's one called Creative Floss that I personally am affiliated with, that we work with a lot of companies trying to set up data infrastructure who don't have it necessarily to begin with and don't know really how to get started. We sort of do that stack for them. But in addition to Creative Floss, there's tons of big data consultancies that help people get off the ground from not having any data infrastructure to having a fully fledged operational data platform. People generally complain that Spark is expensive. This is again due to the in-memory operations that Spark performs. This is true, but I think the costs are quite manageable if you do two things. One, use spot instances as opposed to on-demand. So spot instances are where you can essentially bid for downtime on other people's compute resources, and then use them when they are not. When this is happening, the prices generally are quite cheap. So if you use spot instances for workloads, of course, that can be terminated. So this is what I mean by fault tolerant. If the job can't die, then obviously don't use spot. But if it's ad hoc number crunching and you don't really care whether your job dies, spot instances are a great way to save a lot of money. And most tools like Databricks and Q will allow you to choose Spark clusters that run on spot instances. You can also use very aggressive auto-scaling policies to dial the clusters back down and not have them idle as long. I think clusters are very expensive when they're idling because they're literally doing nothing. So in that, when it comes to justifying the costs of a cluster, it's a lot easier to justify an expensive workload if it's actually producing something of value. If it's not, then you should probably rethink your workloads. And one great way of accomplishing cost reduction accordingly is scaling your resources back down to zero, so that you don't burn through your credits. I often hear a lot that Spark is not as efficient as a certain tool X for a certain process Y. This is true. Again, it's not a silver bullet for all data problems, but given its flexibility to accomplish everything from machine learning to streaming to big data analytics to ad hoc tooling, Spark is a great all-rounder. Its feature set is constantly growing, and the Spark execution core is always being refined and optimized. So it will, of course, get better with time, and generally I've not found it to be a huge bottleneck. And the alternative of using a bunch of different tools and creating what I like to call service mesh, and trying to maintain that is not fun. And the cost associated with that will potentially negate any of the benefits of the performance gains you might see by using certain niche tools to accomplish specific parts of your data stack. Spark is difficult to tune and optimize. This is true. There's no way around it. Spark is quite complicated. So I liken it to trying to fly an ancient fighter jet. As you can see, the cockpit on the right there. Quite complicated. But like the fighter jets, when executed properly, the results can be quite amazing. And there's a lot of new utilities coming out to make this process easier to accomplish. Things like Spark Lens, which is a utility released by Qubel, is a great way of profiling Spark jobs and seeing if you have certain asymmetric workloads. And then you can then go to your resident Spark guru, who will then use his or her tribal knowledge to figure out how to interpret the Spark Lens outputs. So admittedly, it is quite challenging, but this only comes into play, I would say, for very complex edge case workloads or just truly massive workloads. For the vast majority of workloads, reasonable default parameters will get you pretty far. And that's the end of the presentation. Thank you so much for your time. Really appreciate it, the opportunity to tell you more about Apache Spark, and open to hearing your questions.